problem that I'm calling sort of looking at an amplifier that has sort of capacitive feed through. But I also want to think about it from a different standpoint, that many times we've had cases where you'll build an amplifier and or even a logic circuit, and you'll realize that you'll put in a step response in and you'll see some sort of like what people say is an overshoot or something changing like that. And people will go, oh, I wonder what that is. And often there's like various complex explanations that happen. But I want to give like one very typical and very simple explanation to kind of get a sense of it. And it entirely depends on sort of thinking what would be a typical amplifier with capacitive feed through on it. And so I want to set up this problem, which is an interesting problem to take a look at, which is to assume at the core of it actually is a very simple amplifier. For those of you looking at it closely, you might notice it has some feel of a amplifier that might be having a gain of 2, or it may be a lot larger with 2 resistive feedback setting that gain of 2 for you, but also sort of accentuating the fact there's some capacitive feedback between the input and the output. There's a capacitive node there, and then there's a capacitive element here. Now this is very nice. It's still a very nice first order system. And we can talk about all sorts of things about this first order system. And this capacitance behavior here is going to be very, very important as we take a look at the circuit. Now, to probably make this thing easier to start with and realize what's in the green box can be basically combined into a simple one-port kind of structure. If you kind of include the input voltage into it, you can kind of say, let's kind of reduce that down to simplify it. And the circuit you would get would look something like the structure you see down here. Again, the voltage 2 resistors, looking at a voltage source here that then sets that current source. A very simple model of what an amplifier would look like. And again, a very straightforward linear circuit of which you can solve. Usually the easy way to handle this is to say I can deal with KCL at this node, which then gives me this equation for V in terms of V1 and VA. VA is the port voltage at that node. And from that, I can take it one step further and say, all right, this is great. I can also then ask what's the current, which is again a form of a KCL of this node, which is going to be both the voltage controlled current source and the resistance and the sum of the resistance chains. And then what you end up getting is you do a little bit of algebra, you get both of these 2 points. Now the nice thing is that you can see very quickly what that equivalent resistance is for that Thevenin equivalent. You can also realize by setting this equal to 0, you actually can solve for what the source would be at VA. Whatever VA is that value. That's really cool, because now what you end up seeing is I can solve for that. It gives me sort of a minus 2 GMR is kind of the important term here, minus 1 over plus 1. Very interesting little term here, because if GM times R is much larger than 1, and in this case, for the numbers we threw out here, for example, as example numbers is like 100, well, then that basically is 2 numbers that are very close to 100 over each other, cancel out, and you get just minus 2. And so you would imagine that in this particular case where it's much larger than 1, I'm going to get a case where this is going to be relatively minus 2, which again, if you think about feedback of resistors across, say, an op-amp circuit, this is not surprising, or a transconductance amplifier, same idea, right? So we're not shocked that this is the case. And then I can look at what is that equivalent resistance. Well, it turns out this is a large quantity, but it's 1 over a large quantity, so that's very small. I'm just going to ignore that. I get 3 over GM. And that gives me sort of a starting point in terms of the numbers. Okay, so this gives me a very easy and straightforward term of which I can manipulate. Either if I take the numbers that we were working with before, that gives me 3 kilo ohms, just so that way if you want to work with the numbers, you can see what I'm doing with this. And so then you take that, you build that, and then we build the rest of the capacitors. Now, this part gives me the sort of minus 2 Vn and 3 over Gm term as my resistance. But I also still have Vn coming in through that capacitance, and then a capacitance to ground. So I have this as my sort of core circuit. And realize I can always take an input voltage and, if it's going into 2 nodes, I can split that source into both of those paths. So there's nothing really surprising here of what I'm doing, okay? But it still turns out that I still have 1 node that basically is sort of first orders. It's a first order structure, just resistor and capacitor, nothing particularly crazy. But one thing to notice is that from V in to V out, if I don't pay attention to this resistance, this is a voltage, this is a capacitive voltage divider, and we know that that gain is going to be a half because I've made both C's equal. So I'm expecting that's going to probably show up in this conversation. Well, where is it going to likely show up? Probably at really, really high frequency for really high changes. And for small changes, both the capacitors turn out to not be important, and I'm mostly just going to get the 2V in going through to V out. Okay, and it's minus 2V in. Well, what happens when I write that? I can put the whole differential equation here, set up tau, which gives me a tau of 6 milliseconds here. All good, which is about 26.5 kilohertz is that sort of corresponding frequency to 1 tau. And so then I can actually write down, sort of simplify the differential equation to a canonical form. I have the taus, I see the 1/2 in front of the capacitive coupling term for V in. I see a minus 2 for the additional driving term. So it's already sort of feeling about right there. I can look at both my transfer response, transfer function, which is H of S, which basically just gives directly down here. I could have actually solved for this directly from this equation as well, realizing these are both SC, would have worked just fine. Or I could get H of J omega. So that gives me a sense of frequency response. And we're going to come back to this one or two spots here. But what's interesting when you look at this is that I have both step response, and if I solve for the step response for this, what I get is a nice interesting jump up to actually 0.5. This is for a 1 volt input going from 0 to 1. So you might say 1 volt times U of t. And then it's going to fall all the way down to minus 2 with a certain time constant. You see this characteristic jump up that comes up exactly from the capacitance increase. It follows with a gain that is positive, and it's a half, and then it goes negative down here with a gain of minus 2 on the signal. Interesting enough, you look at the frequency response, you do see at low frequency it's minus 2, going all the way to 0.5. And so this works out very nicely with the different corners all the way through. The corner frequency at 26.5. Notice also something else here on the phase, that the phase starts at pretty close to pi, and a pi phase means that I've got basically a minus sign. And on the other side, I get a phase that is, well, basically near 0, and basically is at 0, and therefore, basically I have in that case it basically has no negative sign, so it's going to be exactly a gain that's non-inverting. And so what I like about this is that this kind of shows a number of cases. It's good to really see a lot of these capacitive coupling effects and see that you have both capacitive dividers and resistive circuits, but it also really explains a lot of things that you see in terms of some of these capacitive jumps that often show up in a whole lot of different amplifiers.